Hello, my name is Andrew Knudsen. This is my project about calculating the third-degree p-series, one step closer to finding the sum. So for a little crash course in calculus, a p-series is like what I have up here. So it's an infinite series from 1 to infinity of 1 over n to the p, where p is an exponent that could be any number. So in calculus, we learned that if p is less than or equal to 1, then the series diverges, which means it doesn't have a sum that you can calculate. And if p is greater than 1, then it converges, so you can find one number. So the problem is that test that we use doesn't give you the sum. So nobody actually knew the sum of these p-series until the 18th century with Euler and the Basel problem. So the Basel problem is 1 over n squared. So by making up equations and comparing them to Maclaurin series, he was able to determine that it was equal to pi squared over 6. But unfortunately, the method he used only worked for even-powered p-series. So even today, nobody knows the sum of the odd-powered p-series. So that's what I set out to do. So first, I kind of tried to model mine off of Euler's approach. So I've written the p-series up at the top, and then I created p of x here, which is kind of similar to Euler's p of x, but instead I modeled it so it looks like a difference of cubes rather than a difference of squares in order to compensate for the cube of the p-series. I created this f of x because for some properties we need, f of 0 needs to equal 1, also needs to have an x cubed term. So I recognize that that is the Maclaurin expansion for sine of x plus 1. And from there I just found the zeros of sine of x plus 1, which you can see here at the bottom. So what I did next was I plugged all these zeros into this function up here. And then after doing some arithmetic up here, you can see the difference of cubes. So from there, I'm able to take the x cubed term from the original f of x and set them equal to all the x cubed terms of this function. So after doing more arithmetic, you can see this answer here. Unfortunately, this is not correct. There are a few errors that were made. For one, I did not take into account the multiplicity of the zeros of sine of x plus 1, like Jennifer was referring to earlier. Also, the function I had created, my p of x, doesn't always work because I realized if you have roots that are positive or negative of the same value, then they will just cancel out. So I tried a different approach next. So I tried using partial sums. So I tried subtracting 1 over n to the 6th from the original series. So the purpose of that is you can see that a lot of the terms will cancel out because you can turn the terms of 1 over n to the 6th into 1 over a perfect square cubed. So you can get rid of all those terms from 1 over n cubed, and then you can just subtract the known sum of 1 over n to the 6th, which is pi to the 6th over 945. So although this is correct, unlike my last attempt, it wasn't effective because I wasn't able to produce enough series that would cancel out all the terms from 1 over n cubed. So my final attempt was to use the integral test. So what the integral test does is it determines whether a series converges or diverges. So what you do is you take the series and you rewrite it as an integral in terms of x. And after doing a bunch of calculus, you get that the answer is 1. So this does not mean that the series converges at 1. Just the fact that I got an answer that wasn't positive or negative infinity means that the series converges. So I realized for the p-series, the answers from the integral test actually create a pattern. So 1 over n cubed is 1/2, 1 over n to the 4th is 1/3, etc. So I thought maybe I could use these values in order to find some kind of pattern to find the sum of 1 over n cubed. So I created an equation up here at the top. And m equals the answer from the integral test. K is a constant. N is the degree of the p-series, so we're raising pi to that power, and then we're setting it equal to a, which is the actual sum. So I can only apply this even-powered series because if I tried to apply the odd-powered series, I'd have 2 missing variables, so that wouldn't work. So what I did was I wrote out all the k values for the even series, so they're in order from 1 over n squared to 1 over n to the 4th. After that, I divided a, which was the actual sum, by these k values, and you can see there's another pattern. So following this pattern, you can assume that for 1 over n cubed, which should be right there, we can say that that would be pi cubed over 2. This can also be proven because if you divide k from the original equation, the answer from the integral test, which is 1/2 times pi to the 3, should equal a over k. So, assuming that the sum of the series is actually a rational fraction multiplied by pi cubed, we now know that the denominator is divisible by 2, because as you can see here, all the denominators here are divisible by these ones here. So if I had written pi cubed over 2, it'd be safe to assume that the k value for 1 over n cubed would be divisible by 2. So just another pattern I recognize. So if you list out all the k values for the even series from 2 to 20, you can see that each denominator is divisible by 3 in different increments. So the first 2 is divisible by 3 to the first, the next set of 3 is divisible by 3 to the third, and then it keeps going up. Each set of 3 goes, the degree goes up by another 3. Also, you can see that each denominator either has 2 to the first or no 2 at all. And another pattern I realized was with the 7s, so starting with 1 over n to the 6th, there's 7 to the 1. And then the pattern goes where you subtract 1 from the exponent and then add 2. So you would technically have 7 to the 0, which is 1. Then you have 7 to the 1 and 2. And then the pattern continues where it goes down 1 and up 2. So although I didn't solve like what I set out to do, finding the actual sum, I was able to find some results, like knowing that the denominator is divisible by 2 and recognizing these patterns. So thank you.